Hello class. So in this video, we'll continue on section 6.1. Before I enter into the video, let me make a note. Here in theorem 1, where I gave you the Laplace transform of a bunch of common functions, the book actually gives you the domains of the Laplace transforms. Right? So this table I actually got from another book, and in that other book, they don't give you the domains, but in the book that we're using in this class, they do give you the domains. So I'm just gonna add, all I did was here add in red the domains of each Laplace transform. Remember, the domains mean not the domain of the function f of t, but the domain of the function f of s, right? Whatever's on the right-hand side of the Laplace transform. So they're very, very easy to remember. And again, you don't have to memorize this. I'm going to give you this in the homework, or you can just see it in the homework from the notes, or I'll give you a table of common theorems you're going to use for the exam, right? So you don't have to memorize this, but either way, it's easy to see. For most of them, it's s greater than 0. For e to the at, this were already calculated before, that s has to be greater than a. So really, the only new ones are the ones for the sine, cosine, and the hyperbolic sine and hyperbolic cosine. So for hyperbolic sine and hyperbolic cosine, you have the domain is s greater than 0. For sine and cosine, sorry. And then for hyperbolic sine and hyperbolic cosine, the domain is s greater than the absolute value of k. So that's the only one that's a little bit tricky. I might give you, this would be a good exercise for you to determine why the domain is s greater than the absolute value of k. So I might ask you to do that in the book, in the homework. But for now, again, you don't have to memorize this. You just have to know, okay, these are the domains. Now, the table in the book also gives you the Laplace transform of other functions. I'm not including those because I don't think we're going to use them. If we do, for example, in the homework, I would just give you what the Laplace transform of that function is, unless I ask you to compute it by hand. And if I want you to use it in the exam, I would include it in the table in the exam. Okay. So don't worry too much about the other functions that are given in the table in the book. For the most part, we're just going to be using these functions here. So again, just a little addition to this theorem. Now, let's go back to the video. In the previous videos, we talked about the conditions required for us to know that a function f has a Laplace transform, right? So there were two conditions that guaranteed that a function had a Laplace transform, and those were that your function f has to be piecewise continuous on 0 to infinity, and that it has to be of exponential order. Right? So we went over a lot of examples of exponential order. Again, in practice, all that means is that your function f grows at most as fast as a constant times an exponential. And piecewise continuous, we also went over an example. All that meant is that if you can divide the domain of this function into intervals, as long as your function is continuous on each subinterval, then your function is piecewise continuous. Right, so I gave this picture, this drawing. And then finally, for us, since most of the functions we're going to be working with are continuous, we have to remember that continuous implies piecewise continuous. Right? So if our function is continuous, it's already given that it's piecewise continuous. Right? We also made a note that you would use this theorem in a problem in which I could ask you something like, determine that the Laplace transform of this function exists without actually computing it. That means you have to use this theorem. You would have to verify that two conditions are satisfied, and then you're guaranteed that the Laplace transform exists. And in example 4, we went over examples of that, right? We found how to determine that the Laplace transform of 1 and the Laplace transform of e to the at exist. So we went over all the work for that. Okay. Now, we're going to work on this example. So this is starting the new content. Now, I think this is section 6.3, but I'm just going to include it in section 6.1. But we're going to cover section 6.3 anyways, so we're going to get to it eventually in the book. But for now, I'm just going to say, okay, this is still part of section 6.1. So find the Laplace transform, if it exists, of f of t, where f of t is given by 0 on the domain 0 to 3, and 2 on the domain t greater than 3. Okay. Now, before we determine, or before we compute the Laplace transform, we can easily check that this function actually has a Laplace transform. Right? First, we can ask, is it piecewise continuous? Right? So look at both domains. And so right now you can, let me draw you a picture of what this function looks like. So the function goes from 0 to 3, and on those values, the function is just 0. Oops. on those values, the function is just 0. And then from 3 to infinity, the function value is 2. Now, in both of those domains, right, in domain 0 to 3, the function is a constant. Constant functions are continuous. And on the domain 3 to infinity, the function is again a constant, in this case 2, which again is continuous. Right? So in each subdomain, the function is continuous, so it is piecewise continuous. Moreover, since it's a constant function, right, it's constant in one domain and a constant in the other, of course it grows slower than an exponential, right, because it's not even growing. Right? It grows from, from t to equals 3 to t greater than 3, it jumps from 0 to 2, but other than that, it's not growing. It's just a horizontal line. So of course it is growing slower than an exponential function, so it is obvious that it is of exponential order. So again, without going through all the work, you can just do an argument like that to say, okay, it is obvious it's of exponential order. Okay, so it's piecewise continuous, it's of exponential order, so we know that the Laplace transform exists, right? So we can go ahead and calculate it. Now, how would you calculate the Laplace transform of a piecewise function? Okay. Let's go ahead and use the definition. So the Laplace transform of f of t, by definition, is going to be and let me just go to the limit part. And I said you could do that. You could just go immediately to the limit part. It would be the limit as b approaches infinity of the integral from 0 to b of f of t times e to the negative st. dt. Now, how can we compute this integral when f is defined piecewise? Well, here what you can do is do what you learned in Calc 1. What did Calc 1 tell you? Well, one of the theorems that you learned in Calc 1 is that, and let me explain it this way, if you want to find the area bounded by a function, it's the same as calculating the area bounded by a function on each subinterval. Meaning that we can just calculate this integral on the interval 0 to 3, right, and then add the area on the interval 3 to infinity, which is the same as saying adding the integral from 3 to infinity. Right? And this is just something that you learn in Calc 1. You can break up an integral into its different subdomains. So in this case, applying it to this problem, what this means is that this would be the limit as b approaches infinity. Let's break up the integrals. So one integral goes from 0 to 3. Right? On this interval, the function is given by 0. So we have 0 times e to the negative st plus, now we add the area bounded by the function on the interval 3 to infinity. Right? So for us, it's going to be the integral from 3 to b. Right? And the fact that we're taking this to infinity is accounted for by the limit. Right? Of, okay, what's the function in this interval? On this interval, the function is 2. Then we always have the negative st dt. Now the first part is a constant, right? Because this integral here is going to be a constant. So the limit of a constant is just itself. So this becomes the integral from 0 to 3, 0 to times e to the negative st dt, plus the limit as b approaches infinity of the other part. And this is how you deal with piecewise functions. So you basically just partition the domain into each subinterval and calculate the integral on each subinterval. Now, let's see what we get. Any function times 0 is 0. The integral, the definite integral of 0 is just 0. You can see it here. You can think of, there's no area bounded by this function, right? Because it's just a 0 function. So that's one way you can think of that. Right, so this part here, the first part is going to be 0 plus, now let me move the 2 outside because it's a constant. We can move it outside of the integral and of the limit of, oops. Okay. Now we can just go ahead and calculate this integral. I know you know how to do this, so I'm going to do it a little bit fast just to finish out the problem. So this is 2 times the limit as b approaches infinity of, so we have negative 1 over s, e to the negative st, evaluated from 3 to b. which is equal to, right, just plug everything in. So negative 1 over s e to the negative s times 3, or 3s, plus 1 over s, because we're subtracting, right? So minus minus is plus, e to the negative sb. Again, if we assume that s is greater than 0, we know that this part, let me use another color. We know that this part is going to go to 0. Again, assuming that s is greater than 0. Right? So this would just become 2 times the limit of this part. This is a constant, right? Because there's no b's involved. So this ends up being, so it's a constant, multiply that by 2, negative 2 over s, e to the negative 3s. With the condition that s is greater than 0. And that's how you compute the Laplace transform of a piecewise function. Okay? So very straightforward. Just use what you learned in Calc 1, where you partition the integral or the function into each of its domains, and you partition the integral correspondingly. Okay? Now, on the next video, we're going to start on section 6.2. Remember, the goal of all this is to be able to simplify differential equations. Right? So we're almost there. There's 2 more things we have to see. Right? The first thing is how to deal with the inverse of a Laplace transform. And second, how to take the Laplace transform of derivatives. So we're going to do all that in the next videos.